Okay, so we denoted by Kn the set of all S in 2n or such that S minus all possible covariance matrices of Gaussian state. Then we proved few things and we were in the following proposition. S is in Kn if and only if. Actually, I proved only one way, I didn't prove the other way. So we'll prove that if and only if S is equal to 1 by 4 L transpose L plus M transpose M for symplectic or spin, something in the spin group. Okay. Further, S is so okay. Let's see this digression. Kn is convex is clear, I think, because S minus Ij greater than or equal to 0, then 1 minus lambda S plus lambda S. Okay. Lambda S, but if you do the same thing, it will become Ij only, right? I mean, if you use lambda, it's the same thing, lambda 1 minus lambda plus lambda, which is Ij. This is, of course, you can write it as minus 1 minus lambda Ij minus lambda Ij. Okay. Now you can add those things and that is greater than equal. So this is clearly convex. Okay. And the definition of an extremal point. So a point, so let what is the C be a convex set. C be a convex set. Okay. Maybe I will write it here and then go to this definition. Okay. Further, S in Kn is extremal if Kl equal to M. If and only if S is equal to 1 by 2 L transpose L. For some Ln Sp to M. Okay. So C is a convex set, then an element X in C is extreme, is said to be extreme. If X is equal to 1 minus lambda X1, or it is, it's enough to take midpoint actually. If it is lies in a, then you get something in the mid, 1 by lambda X1 plus lambda X2 for X1, X2 in C and lambda in, if it is lies in the line joining some X1 and X2, lambda in 0, 1, then X equal to X1 equal to X2. Okay. This is what the property of extremal. So there is no line which contains that point. Okay, line containing in this, it should be a point itself. Okay, that's what extremality means. Actually, it is enough to take midpoint. I mean, X lies in the midpoint, then it is like this. It's enough to, one can say that. That is easier. Or in the proof itself, you can write whatever the proof I'm going to prove, you can write 1 minus lambda lambda. It will be unnecessarily complicated, but you will get the same thing. So there is no problem. Okay. Anyway, so first we want to prove the following, the proof of the proposition. So S is in Kn. Then we proved S is equal to, we have already proved using Williamson form and other thing, 1 by 4 L transpose L from M transpose M for Lm Sp to N. So now the other way, to prove the other way, suppose, so to prove the other way, there are two ways of doing it. One way is, I mean, this S which satisfies that condition S minus Ij, 2S, there should be 2S, I'm sorry. I mean, it's equivalent to consider both of them, but since we are considering particular part, this 2 is important. So all those matrices which satisfy this 2s minus Ij greater than or equal to 0 or Gaussian state, Gaussian covariance matrix of Gaussian state. So you always have this Gaussian state gamma of L or L inverse of E of 0. Okay, you take the pure state corresponding to that. I mean, write the same thing here. You take the state. You take the state corresponding to this pure state. That will have the covariance matrix L transpose L, half L transpose L. Okay. So we already have that. So that is enough. Or you can directly prove this positivity condition because you have this identity matrix, which is going to be this identity 0, 0, identity minus I by 2. Yeah, I by 2 only, no? Yeah. So 2 times z minus I by 2 j. This is certainly greater than or equal to 0. You will get I by 2 there, and okay, this is greater than 0, right? So you can put a L here, L transpose here, L here, which is also true. If you put L transpose L, you get J only there. Okay, because it's symplectic. So this is greater than or equal to 0. And this implies L transpose L. Half should be there, no, somewhere. There should be half somewhere, no? Oh, okay. So this itself is true. Without the 2 itself, it's true, right? That's also true because the determinant is just 0, right? If you take the determinant of I0, 0, I minus Ij, that has determinant equal to 0, right? So that implies L half L transpose L itself. So this is true. This is true. Okay. So, but that implies 1 by 2. How does that imply half L transpose L is that? I want to prove that. Eh? I don't think the determinant will be 0. No, determinant of this will be 0. No? I0, not this, that. 0I minus Ij. This is 0, no? Oh, Ij, yeah. Yeah, this is 0. So this is, but still this is positive. Determinant equal to 0 is, determinant greater than or equal to 0 is positive. Okay. So this is still positive. It may have some kernel. Okay. Still it's positive. It's not strictly positive, but it's positive. So by conjugating with L transpose L, you still get this. That is right. So our condition is 2 times that has to be. So this implies L transpose. This is just, I mean, this is just L transpose L half, right? L transpose F half minus Ij is greater than or equal to 0, correct? So this implies half. I don't know, I was unnecessarily confused. This is in a K, that's all. That's all. No, I was wondering about L. It's not L by 2. It is just half of L transpose L. That's no problem. So this is, so we approved the proposition. Okay, it is done. Now we want to worry about the extremal. Okay. So suppose S is equal to L half L transpose L plus M transpose M in Kn is extremal. We have proved that S is in this form. Suppose if it is extremal, then we know that half of L transpose L, that is a, I mean, that is a Gaussian, that is in this. Okay, we already know that. Why did I say this? Oh no. I haven't proved. So what? No, we are proving the other way. Sorry, we have, let's go one by one. We were proving this. S is equal to 1 by 4 L trans, S is in this form. Okay, if S is in Kn, then it is in this form. If it is in this form, it is that is in Kn, we want to prove. Okay. Now for any symplectic matrix, we have proved that half L transpose L is in Kn. Similarly, any for M also, L and M. But then this is convex. Since Kn is convex, that is how it follows. Kn is convex. Any half L transpose L from M transpose M is in K. Okay, that's what we want to prove. If it is in this form, then it is in Kn. If it is in Kn, it is in this form. Okay, now we come to extremality. Okay, so suppose some Kn is in, sorry, S in Kn is extremal. Okay. So S will look like then S is equal to half of L transpose L plus M transpose M for L and M symplectic matrices. But then we already know that this is in Kn, that is in Kn. I mean, 1 by 4 here. So we know that this by 2 is in Kn by 2. 1 by 2 of this is in Kn, and 1 by 2 of that is also in Kn. So this is just the linear combination of this. So L has to be equal to, maybe I'll write it. Since half of L transpose L, half of M transpose M, both are in Kn, L transpose L should be equal to M transpose M. That's all. L need not be equal to M transpose M. We have already, because it's extremal, it cannot be written like that. Okay. So S is equal to half L transpose L. Okay. Now we have to prove the other way. If it is in the form of L transpose L, then it is extremal. We have proved that if it is extremal, then S is equal to half L transpose L, because it cannot be a convex linear combination of two things. Okay. Now, if S is equal to half, now what do you want to do? We want to prove that if S is in the form of L transpose L, then we want to prove it's extremal. Okay. So suppose, as I said, we will take the midpoint in the definition of extremal point. So suppose S is equal to half of S1 plus S2. Okay. But then S1 and S2 will look like half of L1 transpose L1 plus 1 by 4 here. L2, M2. Let's put L1, L2. Okay, L2 transpose L2 plus L3 transpose L3, which is for S2. For the other one, S2, L4 transpose L4. Okay. So S will look like 1 by 4 summation I. Li transpose Li, where each Li is in SP to N. Okay. 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 Which is equal to half of L transpose L. Now this implies 1. Identity is equal to 1 by 4. This is 1 by 4. So 1 by 2, right? Okay. 1 by 2. So identity equal to 1 by 2 summation over I. L transpose inverse of Li transpose Li, L inverse, right? We can write it like this. Okay. You call those things as Mi. Summation Mi. You call those things Mi. Okay. Now it's all product of symplectic matrices. Symplectic Mi is also in. Mi is also symplectic. Mi is also is the spin group. Okay. Now what do? I want to write it for the inverse. Okay. Now you multiply by J. J is equal to half summation I. So I multiply by J somewhere. JMI doesn't matter, I think. JMI. But MI is positive, self-adjoint in particular. It's transpose itself. So we will get half summation I MI inverse, right? J inverse is L inverse, L transpose inverse, right? J. L for any symplectic L transpose J, L is equal to J. Okay, now transpose is same, so it will be, you take it to be L itself. So this implies JL is equal to, it will come, the L will go to the other side as inverse, right? Pass through the symplectic, self-adjoint, symmetric symplectic matrix will pass over the J as J inverse. Okay, so I got it M inverse equal to J. Okay, and M inverse equal to J, and I have the J here. Okay. Now you can remove the J. Okay, this
how do we know it's symmetric?
L transpose L. It is in the form of something transpose something, no?
Yeah.
No, no.
Yeah.
Here I made a mistake. I have written there correctly. This is Li transpose inverse. Okay.
Yeah.
They are all symmetric. Okay. So this implies half. So 1 is equal to again half summation mi inverse. Okay. Summation mi is also 1. Summation mi inverse is also 1. So now we compute the following. Mi are positive. I mean, it's something transpose something. So it's positive. So it has a square root and it's invertible. So it has the inverse has a square root. If something is positive, the inverse is also positive. So power whole square summation over I. So this will be summation mi, the summation mi inverse minus 2, right? Okay. Minus 2, right? Yeah. And that it should be 1 or 2. Summation mi equal to 1 or 2. Why am I getting a 1 here? Summation inverse or summation mi 1 by 4. Oh, sorry. Here it should be half. No, there is a half there. S is equal to half of S1 plus S2. There is a half again outside. Right? Okay. So, so, yeah. So where is the mistake? S is equal to half of that. Okay. So there is a half L transpose L is equal to half. So you cancel the half both sides. So it will be 1 by 4. Here there will be 1 by 4. So half into here there is a half. I missed that half. Okay. Okay, so it should be 1 by 4. 1 by 4. Okay. So summation mi equal to how do we get 0 here? I want to get 0. Summation mi, summation mi inverse. Oh, this should be 1, that should be 1. So where is 1 by 4? Summation mj equal to 4. Summation 2mj into mj minus inverse is 2. This is silly. Why should we get no, this two oh. This is summation mi is 4, summation mi inverse is 4. This 2 will be 4 times now. That's all.
Yeah.
Yeah. So totally it's 0. Summation mi is 4, summation mi inverse is 4 plus 4 is 8. And this 2 will occur 4 times, right? put a bracket. Okay, that is equal to 0. 8 minus 8 is 0.
I can't see.
Sorry. Sorry. Yeah. No, 1 by 4, summation mi inverse is 4. Summation mi is 4. I just kept the 2. 2 will occur 4 times. That's all. Okay, that is a problem. Okay. Okay. Summation mi is 4. Summation mi inverse is 4. And the 2 will be there 4 times. Okay. So because of that, this is 0. Okay. Now, if you have sum of positive elements which are 0, the square is of course positive. Okay. They are self-adjoint elements. Whatever inside is self-adjoint. M power of minus M power minus of is self-adjoint. Square of a self-adjoint is positive, right? Square of a self-adjoint is positive. Of course, you can write the equation. It's clear. It's positive. Okay. And sum of positive element is 0, means it is 0, right? If you have some, let me verify it for 2 elements. If A1, A2 both are positive and A1 plus A2 equals 0, then both A1, A2 should be 0. That's because A1 xi plus A2 xi both should be equal to 0. They are positive numbers, so both should be equal to 0. Okay. Now A1 xi equal to 0 means A1 norm of A1 power half xi square is equal to 0. Okay. I mean, this is how we should argue. Okay. So A power half is actually 0. Xi has this is 0. So A norm of A1 power half is 0. 0 operator. So its square is also 0 operator.
You can't just say because.
No, that we can't say because it is real.
Oh, it's real.
Yeah, in complex, that is where you have to go through. In complex thing, if A1 xi equals 0, then A1 is 0. Okay, this is this is real. So real, you have to argue like this. Yeah, that's right. Okay. So because of that, A1, A2 are 0. So this implies what? This implies mi inverse. So from whatever we have mi is equal to mi inverse, right? Okay. Now mi power half is equal to mi inverse. So this implies mi equal to 1. Okay. All of them equal to 1. So, but mi is some L inverse transpose something. So these things imply L transpose L, okay, is equal to Li transpose Li for all I. That's all we want. That's what we want. Okay. I mean, you will submit 4 times and divided by 2 is half. Okay. So we approved this. Now another corollary or another proposition. If S1, S2 in Kn, both extremal, both extreme points, you can't compare two extreme points. That's what this says. And using the operator partial order. If S1 is greater than or equal to S2, then S1 equal to S2. So proof. So S1 equal to half, because they are extreme, L1 transpose L1, and S2 equal to half of L2 transpose L2. Okay. So S1 is greater than S2. Okay. Which says that L1 transpose L1 is greater than L2 transpose L2. Okay. Now they are invertible. So you can apply L1 inverse and L1 transpose inverse on both these things. So which implies L1 transpose inverse, L2 transpose L2, L1 inverse is less than or equal to identity, right? Okay. I mean, you can do this. See, you can preserve S1 greater than or equal to S2 means what? S1 minus S2 is greater than or equal to 0. If some A is positive, then you can conjugate by 2 a transpose matrix and B transpose A, B is also positive, provided the middle one is positive. Okay. So the positivity is preserved by this conjugation. Okay, that is why we are doing this. Okay. You can put the transpose here and you can put the other operator here. Okay. So this is less than or equal to 1. But on the other hand, this is symplectic. So symplectic means its determinant is 1. If either lambda, the eigenvalue lambda is 1, or if lambda is not equal to 1, if lambda is an eigenvalue, 1 by lambda is also an eigenvalue. But that's not possible because all eigenvalues are less than 1. Okay. If this is less than 1, this implies spectrum of that is contained, spectrum of that operator is contained in 0, 1. Okay. But then since symplectic, if lambda, for symplectic are for elements in SP2NR, because we are not working with complex space, we have to use this SP2NR. Lambda is an eigenvalue. Lambda is in the sigma of that, implies 1 by lambda. Lambda inverse is also in the sigma of that. Okay. But that is not possible because it's all contained in 0, 1, unless it is identity. Okay. So that is simply, that is identity means L2 transpose L2 is equal to L1 transpose L1. That's what we can, L1 need not be equal to L2. These two are true. So this implies S1 equal to S2. That's all. Okay. Now we have got almost everything to write the general form of a Gaussian state. So the Gaussian state, we have already noticed that the mean is not a problem. If you have any, if you have got a Gaussian state with mean 0, then by conjugate by a Weyl operator, W of alpha, you get a with minus alpha or whatever, doesn't matter. So you get any mean you want. So getting all the covariance matrix is the only non-trivial problem. So now we know that I mean, I don't know how to write the whole thing. So if you have any Gaussian matrix, so if rho is Gaussian on L2 of Rn, okay, then rho is equal to W of alpha, some rho naught, W of alpha inverse, okay, for some rho naught with mean 0. Okay. Now we have to only worry, we have to say what is the general form of rho naught. Okay. Okay. So the rho naught has the, okay. Now we know that the Gauss, so what is it? We want to get So suppose if S is a Gaussian matrix, I mean S is in Kn, okay, S is a Gaussian covariance matrix, okay, then S is equal to L1 some L D 0 0 D L transpose, right? This is the Williamson form. Okay, the Williamson form. So if we can get a Gaussian matrix, if we get a covariance matrix, Gaussian covariance matrix with that block diagonal DD, then this L transpose will get it by gamma L, right? I mean, if you have, see, if rho 0 S, suppose, I mean, this is the Gaussian state with, this is a Gaussian state with mean 0 and covariant matrix, mean 0 and covariance matrix. Yes, okay. Then rho 0 S, we get it as gamma of L. I mean, L is a symplectic, so we have a gamma L. Gamma L, maybe we put an inverse here, gamma of L inverse, rho of 0, this matrix D0, 0D, okay, gamma of L, right? Right? Because, I mean, you will see, I mean, the point is this. This is the one, no? I know we have to verify something. If we have something row hat of some for a row, then if you gamma of L, we have this formula. Let me just write, I mean, just for the gamma of L rho gamma of L inverse hat is equal to rho hat of L inverse of alpha. This of alpha is L inverse alpha, right?
Yeah.
Right.
Because this movement, the way of it.
Correct. But then here, what we get, no, here I get how I get the conjugation. That's what I'm saying. So this is going to be exponential. You have the mean 0. So this is going to be x sx alpha. I mean, alpha, you write it as the real part, real one, alpha, beta, whatever, doesn't matter. So yes, alpha, alpha. Maybe xy, I will write. Yes, xy, right? Okay. Now this is good. You are going to get L inverse here. You get an L inverse here. L inverse, sorry, inside. L inverse of alpha, no? That's what. S of L inverse of xy, right? So this inverse will come as transpose there, right? Okay. So we get that. I mean, we get that form. I mean, actually, this is only L inverse alpha here, but because there is two times it comes, the transpose will come there. Okay. Is just to notice that. So we only have to, so we know that by using a simplicity, we get this. Okay. Now we only have to produce how to get this row 0. So we how do we get this row 0 D 0 0 D, right? How do we get that? But then D is equal to, D will look like this, right? D will look like D1 up to Dn 0 0, where each Di is greater than or equal to half. Okay. And they are written in decreasing order. So let's assume that the first L of them is strictly greater than half. Then everything is, M of them is, so let D1 up to DL is strictly greater than half, and DL plus 1 up to DN is equal to half. Okay. Now we know how to get a 2 cross 2 covariance matrix. See, the point is 0, this D 0 0 D. This you get it as tensor product of rho Di. Right? Right? Then direct sum of, if you take direct sum of two Gaussian matrices, that will be tensor product of the corresponding thing, right? Okay. So because of that you can verify that. Okay. Because of that you get di like this. So you have to produce only all those di's. For half, we have the vacuum thing that has covariance matrix half times I. Okay. For strictly greater than half, we have already produced that e power. Yeah, if di is strictly greater than half, okay, then take SI take SI such that di is equal to, I think, half cot h SI by 2, right? Okay. Then rho j is equal to 1 minus e power minus SI times e power minus SI a dagger A, where A dagger is, it's one dimensional. Okay, the number operator. Okay, one. I mean, L2 of R, number operator on L2 of R, or Fox gamma of C, Fox space of gamma of C. It's just the number operator. It just gives the number n on the n particle space. Okay, so it is that rho j is this. So we got that row of 0, this D0. And I mean, if Dj is strictly greater than half, if Dj equal to half, then you take row J is equal to this E of 0 itself, okay, corresponding to this pure state. Then this is nothing but tensor product of row J, whatever row J or row I, mixed I and J. Okay, doesn't matter. Okay, J equal to 1, 2. So if the covariance matrix is 0, D, we know how to get it. For any DJ, we can get it. Okay. Now we got a simplex using the symplectic matrix. I mean, then you have to conjugate with the symplectic matrix. Okay. Then you have to conjugate with the W of alpha to get every state. This is how every state will look like. So every Gaussian state will be is of the form W of alpha, gamma of L, then tensor product of rho I. Let me put DJ. I mean, you have to write when DJ is half, then you have to take the corresponding to vacuum vector. Otherwise, you have to take this. So let me just write it DJ itself. Okay. Rho DJ equal to 1. Then again, you get gamma of L, W of alpha. This is how every Gaussian state will look like. Okay. Using a symplectic matrix, using that. That's how it will look like. We have got it. So now we prove the following theorem. Every pure Gaussian state, I mean, the vector corresponding to that in the L2 of Rn is what is called the wave function. Okay? But we will call it as a vector. Every pure Gaussian state corresponds to W of alpha, gamma of U, then E lambda 1, then E lambda 2 Gaussian state on L2 of Rn. Okay. E lambda 1, E lambda 2 up to E lambda n. And lambda can be lambda cannot be 0. It can be just the vacuum state, then the lambda 1 has to be just identity, right? No. We are discussing pure state. Okay, so we are talking about the symplectic matrix. So it will look like no. This is just lambdas are just positive. Lambdas are just positive numbers. So the lambda is greater than 0. Sorry. I'm sorry. I'm getting confused with something else. Sorry. Every pure state. We have seen how a general state will look like. Using that rho dj and using that number exponential of the number operator, that state, and using that we got it. Now every pure state will look like that, where E lambda n is of the following form. E lambda equal to, for any lambda greater than 0, E lambda equal to E lambda at t or whatever, at x is equal to, it's a function 1 by 2 pi power 1 by 4, okay, lambda power half e power exponential of minus norm x power x square or x power 4 x square by 4 lambda square. This is a function. I mean, this is a function which is a vector in L2 of Rn. This is something in L. Oh, this is just. I mean, you don't need norm square. I'm sorry. you can write x square. Because this x is in L2 of R. This is in L2 of R. Right? Let me say it again. Forget about W of alpha, comma of U. For second. But U is a unitary, n cross n unitary, and alpha is a vector in Cn. Then we have W of alpha, gamma of U, acting on L2 of Rn. And that's a vector in L2 of Rn. It's a tensor. So we identify L2 of Rn with tensor product, L2 of R tensor L2 of R n times. Okay. And in L2 of R, it's this vector. Okay. Okay. So proof. See, we have the general form of a Gaussian state. This is a general form of a Gaussian state. Okay. So a Gaussian state is pure if and only if its eigenvalues are 0 and 1. I mean, state is a trace class operator. Okay, so it's a compact operator. So it has nice operator. It has eigenvalues. So it has to be a projection, one-dimensional projection. That's what a pure state is. So its eigenvalue should be 0 and 1. On the other hand, the number operator will have infinitely many eigenvalues. Okay. Number operator will 1 up to n, 1 up to infinity, but e power minus whatever nj, nsj or whatever, e power minus nsj will be the eigenvalues of number operator. It will have infinitely many operator. So we cannot have rho dj for dj strictly greater than half in this expression when it is a pure state. Then the eigenvalues will be, eigenvalues of tensor product is the product and all the, if you go, you can go through all that. Okay. So dj should be equal to half if it is pure. Okay. So if you call this a star, dagger or something. Okay. But you can see the password. It's okay. Why? I'm not installing. Okay, for later I agree. Okay. I said later, I'm still asking all these things. Okay, so suppose rho is a pure state, pure Gaussian state. Okay. Then in star, dj has to be half. Okay. Since the number operator a dagger a has countably infinite eigenvalues. Okay. So we can have only 0 and 1. So dj has to be half for all j. Okay. So rho is equal to W of alpha. Rho, I'm only look at the vector, okay, gamma of L. So rho corresponds to this vector. W of alpha, gamma of L. And then what? Yeah. And then E0, right? E0 tensor n times, right? E0 is the vacuum vector in L2 of R. R E0, it's okay. Okay. Now this gamma L is a symplectic operator. We know that L looks like this. L is equal to U1. If you wish, you write it as a unitary as well as symplectic. Okay. A real unitary matrix need not be a complex unitary matrix. Real unitary matrix of 2n cross 2n need not give rise to a complex unitary matrix. But if it is a real unitary matrix and also it's a symplectic matrix, then it is complex linear and it's a complex unitary. It gives the idea complex unitary. Now, given any matrix on 2n cross 2, any 2n cross 2n matrix, you can identify with a complex function on Cn. It is linear on some condition. Okay, if it is unitary and if it is orthogonal, which is when we use the language orthogonal for real one. So if it is orthogonal and also symplectic, then it's a complex unitary. It gives rise to a complex unitary matrix. That correspondence, tilde correspondence, whatever we had. Okay, so L will look, or if you have L is, I mean L tilde will look like this, for example. Okay, U1 and something A00 A inverse, right? U2. We have this form. Any symplectic operator will look like this. We proved it. Okay, so gamma of L will be equal to gamma of U1. Okay, there's a scalar coming here. That doesn't matter, I think, because when you conjugate, the scalar will go away. You're going to conjugate, no?
Yeah, but it's not directly scalar.
No. What I'm saying is gamma of L, this gamma operator, I proved it's not completely proven that for any symplectic operator, gamma of L1, L2 is gamma of L1 times gamma of L2. So the gamma of the whole thing, if you take, it is some scalar times. There will be a scalar coming here. There will be alpha times gamma of U1, gamma of A00 A inverse, gamma of U2.
And 1 over alpha. I mean, alpha bar will come there.
Alpha or alpha bar, something will come. Some number will come.
Yeah, when you write.
But when you conjugate it, alpha bar will come, it will
So
cancel. So it doesn't matter. Okay, it doesn't matter. So we can assume that gamma L is like this because we are only going to conjugate it. Okay. So gamma of L will look like this. So if you, so this alpha doesn't matter. Okay. Okay. So we only have to work. So our the statement is the following. Statement is, for any pure thing, it will look like W of alpha times gamma of U times that. Okay. So we only have to worry about what is the eigenvalues of this. So suppose A has eigenvalues. Lambda 1 up to lambda n. Okay. Then L is equal to U1. I mean, then W of alpha, gamma of L. See, if you conjugate E0, the vacuum vector, if you apply gamma of U on vacuum vector, you get vacuum vector itself. Right? So one of this gamma U2 doesn't matter. Okay, that gamma U2 will go away. Gamma U2 actually in vacuum vector is vacuum vector. I mean, if you have a pure state, and if you conjugate the pure state with gamma of U, it will be like, or any unitary. If you have a pure state, conjugate the pure state by any unitary, that is equivalent to the applying the unitary on the corresponding vector. Okay. And that is fixed. That fixes E of 0. Okay. So our original states correspond to W of alpha, gamma of L. Gamma of L is gamma of U1, right? Gamma of U1 times gamma of A, which corresponds to gamma of tensor product of n j equal to 1 to n. Gamma of this lambda 0 0 lambda inverse. Okay. Right? It's a tensor product. It's a direct sum of these kind of matrices, so it will be tensor product here. Okay. See this gamma for the symplectic, you can get it from the property. See this gamma of L, as it is defined, is the unitary, not unique up to scalar, the unitary, which satisfies this property. W of alpha, gamma of L inverse is equal to W of L alpha. Right? It is a unique one. Okay. So because of that, gamma, if L has eigenvalues lambda 1 to lambda n, or L is a direct sum of things, the Weyl operator can be written as direct sum. It's a good exercise, you should write it. Okay. L can be written as direct sum. Okay, so L will also become direct sum of a tensor product of such operators. So W of alpha will be tensor product of the corresponding alpha 1, alpha 2, alpha n. Alpha is equal to alpha 1 up to alpha n. Yeah. right? So the L will also be direct sum. So tensor product. No, L will be direct sum. Gamma L will be the tensor product.
Inside will be addition, you can make the tensor product.
Yeah, yeah.
Because
it is determined by this this property, property. Okay. So because of that, we get that it will look like this. So all we have to do now is just calculate this gamma of, but gamma of lambda 0, 0, lambda inverse of E0. So it's acting on E0. Okay. Is E0. E0, we know what is E0. Is nothing but, which is, I mean, 1 by lambda in, you know how it acts on E0. This was in the assignment, right? You have the A inverse outside and determinant outside, and yeah, determinant of A, which is just lambda here. Okay, so which is just equal to 1 by 2 pi power 1 by 4 e power x square by 4, 4 or 2. 2 is the vacuum vector. So you have to get the lambda here and lambda power half here. Okay. So this is how a pure state will look like. Okay. Finally, there is something about the purification. See, I asked you to look at the end of the first paper. There he says something, which is I want to do it as an exercise so that I can, as you said, it can be discussed in the exam or something. Okay. So, let's see. Let me just give a sketch. The next proposition is the following. Any mixed, I mean, only mixed state we should worry. Any mixed Gaussian state on L2 of Rn can be purified to, I mean, there exists a pure state there such that if you take the partial trace, you get this. Okay, can be purified to a state on L2 of Rn, tensor L2 of Rn. Okay. So how to do that? Okay, so I mean, we don't have to worry about the mean. Mean is not a problem. Okay, we only have to worry about the right. Suppose rho is equal to rho of 0s. Okay? Otherwise, we'll have W of alpha there, which we can. I mean, if you yeah. No, but we want to get it pure state so that if you take the partial trace, you should get this state, right? So what will be the W of alpha there? We can take the W of alpha. Okay, let us work it out and then it will be clear. Okay. So suppose rho, then S is equal to half 1 by 4 L transpose L from M transpose M, right? Okay, so this is not a pure state. So we have L and M. I mean, this is not extreme. So I mean, pure is equivalent to extreme there, right? Because it will be L will be equal to M, right? So what we do is the following. We take this state. Okay, let's take rho 1 equal to gamma of L of E of 0. Okay, this corresponds to this. Okay. You call it maybe chi L, the vector. Chi L equal to chi L1, chi L or whatever. Yeah, L and M. Okay. which is equal to gamma of L is 0, this vector. Okay, call this chi L. Now we consider chi L tensor chi M. This is a vector in L2 of Rn, tensor L2 of Rn. Then you mix it. So what you do is that you can see if you have Rn direction Rn. Okay. You can, what you do is you can rotate it. So if you define U0 from Rn direction Rn to Rn direction Rn, you can actually use any theta and to do that. So what we do is U direction V will go to U plus V by root 2. This is by rotating by 45 degree. Root 2. Okay. This is an exercise. If you apply this, then you can use the same technique to find the covariance. I mean, you use the theorem. You can find the characteristic function of this. You will find that this, that is you take this U0 of gamma, sorry, chi L tensor chi M. Okay. Then you take the partial trace. Partial trace means if you consider the characteristic function, it is only the up to first alpha n we have to consider. Okay, that will have rho 0 with covariance matrix x1 plus s2 half. Okay. Or if you have, you can have actually sin theta times u cos theta times v, sin theta cos theta u sin theta v. You can use this matrix.
Rotation.
Yeah, cos theta minus sin theta. You can rotate, use the rotation thing, and then apply this u0. Then you will get cos square theta instead of half. Here it is 1 by root 2.
Yeah.
The theta is, theta is 45. So pi by 4. So you will get cos square theta sin square theta here. This is an exercise in the end part. The end of the first paper.
I read it, but I didn't.
It is very easy. You just apply the same technique. You just should have understood the same technique. It will, from the characteristic function, it will follow. So this will be, if you take the tray, if you take this, then you will get this, which is precisely that. Right? S1.
Yeah.
I mean, where S1 is this, sorry, S1 is the, I mean, this chi L will have covariance matrix L transpose L, half L transpose L, that will have L, M transpose M, and you can mix it and get it. Okay. So any Gaussian state, any mixed Gaussian state can be purified. That's what this says. So we want to talk about some symmetries of Gaussian state. We'll discuss it later. Next week. Okay. Something new. So this side, I'm not giving the complete proof. I want you to go through, write it down. Okay.